Okay, let's balance this equation over here. It's a simple reaction, so I would probably be able to balance it without any specific reference to oxidation and reduction. But please remember, not all reactions are that easy and simple. So we will use this example over here to practice our ability to balance chemical reactions with the help of oxidation and reduction half reactions. I will start this process by assigning oxidation state to everything that I see in this reaction. Okay, with these oxidation states, I can see that my oxygen has been oxidized and chlorine has been reduced. Potassium doesn't have any change in the oxidation states, so it will not be part of oxidation or reduction. It is a spectator ion. In this reaction, oxygen is oxidized. Oxygen is losing electrons, and I'm writing it like this. I have 3 oxygens on the left and 2 oxygens on the right. I need to fix this problem right away, otherwise it breaks the law of conservation of matter. So I will put in these coefficients here. Now I have 6 oxygens on the left and 6 oxygens on the right. Each oxygen with the charge -2 losing 2 electrons to become oxygen with the oxidation state of 0. So when 6 oxygens do that, 12 electrons would be lost as a result of it. Now let's look at the chlorine. Chlorine with oxidation state +5 accepts some electrons and becomes a chlorine with the oxidation state -1. It takes 6 electrons to go from +5 to -1 oxidation state. All right, but we know that 12 electrons got to be accepted, so we need 2 chlorines to accept 12 electrons and 2 ions of the chlorine with the oxidation state -1 will be created at the end. Now I will transfer these coefficients from oxidation and reduction half reactions into my overall reaction, and my reaction is balanced. And while I'm at it, I can report that my chlorine with the oxidation state +5 played the role of oxidizing agent, and my reducing agent was oxygen with the oxidation state of -2. Let's balance this reaction with the help of oxidation and reduction half reactions. We start by assigning oxidation states to everything that we see in this reaction. Based on the change in the oxidation states, we can say that nitrogen was oxidized and oxygen was reduced. Nitrogen with the oxidation states -3 turned itself into nitrogen with the oxidation state of +2. To do that, that nitrogen should have lost 5 electrons. Oxygen atoms went from the oxidation state of 0 to -2. It means that each atom accepted 2 electrons. And since we have 2 oxygen atoms doing that, 4 electrons were accepted. We know that the number of electrons lost and received should be the same, but here we see the clear mismatch. 5 electrons are lost and 4 received. This is a result of the fact that our equation was unbalanced. The least common multiple of 5 and 4 would be 20. Let's multiply oxidation half reaction by 4 and half reaction of reduction by 5. Now I have 20 electrons lost and 20 electrons received. What is left for me is to transfer my coefficients into my overall reaction. 4, 5, 4, 6. Those 10 oxygens with the oxidation state -2 are split between 2 compounds. 4 are inside of the nitrogen monoxide, and the remaining 6 are here in water. Oxidizing agent of this reaction was molecules of oxygen, and reducing agent was the nitrogen with the oxidation state -3. This reaction is simple and easy. Most probably you can balance it without any reference to oxidation and reduction half reactions. But we are practicing to use those half reactions for balancing something more complicated. So let's quickly assign the oxidation states to everything that we see here. From the change in the oxidation states, we can see that the nitrogen is reduced and hydrogen is oxidized. I have 2 hydrogens on the left and 3 hydrogens on the right. That's a violation of our law of conservation of matter, so I can fix it with coefficients. Okay, so now I have 6 hydrogens on the left, 6 hydrogens on the right, and each hydrogen, atomic hydrogen on the left, is losing 1 electron. Since I have 6 of the hydrogens doing that, I will have 6 electrons being released. Now, in this reduction half-reaction, I have 2 nitrogens and 1 nitrogen. Of course, I need to fix it. So I will put the coefficient here. And I know that each nitrogen accepts 3 electrons. So considering that I have 2 nitrogen doing that, 6 electrons are accepted. All that is left for me is to transfer coefficients into my reaction, and to identify my nitrogen as being an oxidizing agent and the hydrogen as a reducing agent of this reaction. I think by now you understand very well that number of electrons lost in oxidation half-reaction should be equal to the number of electrons received in the reduction. So there is one more point that needs to be made about oxidation-reduction half-reactions and oxidation reactions in general. If we have the equation correctly balanced, we should see the conservation of charge. It means that the charge on the left side of the equation should be equal to the charge on the right side of the equation. Let's look at this half-reaction of oxidation. On the left, we have 6 atoms of hydrogen, each carrying the oxidation state of 0. So the charge on the left is 0. And on the right, we have 6 ions of hydrogen with the charge +1, which creates +6, and 6 electrons, each carrying a charge of -1, which creates a -6. 2 of these things together cancel each other out and bring the charge of the right part of the equation to a 0. So we have the same charge on the left and right side of this oxidation half-reaction. Now let's analyze reduction half-reaction. We have 2 atoms of nitrogen and oxidation state of 0 on them. But we also have here 6 electrons, each with the charge -1, which overall creates a -6 charge on the left side of this reaction. While on the right we have 2 nitrogens, each with the charge of -3. Taken twice, it creates a -6. So once again, we have the same charge on the left and right side of half-reaction. Let's quickly run over the remaining 2 reactions that we've balanced today. So here in oxidation half-reaction, we have 6 ions of oxygen with the charge of -2, which creates -12 charge on the left side of the equation. On the right, we have 6 atoms of oxygen, each with the oxidation state of 0. But we also have 12 electrons, each with the charge of -1, which creates a -12. Overall, charge of the right side of the reaction is -12. We have equal numbers, equal charges on the left and right side of this half-reaction. It means that it is correctly balanced. Now let's look at the reduction half-reaction. 2 chlorines with the oxidation state +5 creates +10, but 12 electrons bring it down charge of the left side of the reaction to a -2. If we look at the right side of the reduction half-reaction, we see 2 chloride ions, each with a charge of -1, which creates -2 on the right side of this equation. On the left and right side, we have the same charge. This half-reaction is correctly balanced. Quick check of charges of the oxidation and reduction half-reaction shows me that I have correctly balanced oxidation and reduction half-reactions. Whenever we see oxidation or reduction half-reactions or overall redox reaction that does not obey the law of conservation of charge, meaning that the charge on the left is not equal to the charge on the right side of the reaction, then we are looking at the reaction that is incorrectly balanced. Let's look at this reaction over here. +2 on iron. Adding 1 negatively charged electron supposed to end up with +1, but on the other side of this equation we see +3, not the correct equation. Over here we have iron atomic iron, which is 0, adding 2 electrons, and it's supposed to end up being -2, but what do we see on the other side? +2. So not a correct equation. Over here, atomic iron adding 1 electron, supposed to end up being -1, but we see on the other side +3, not a correct equation. Now, if we look at the correct answer to this question, number 1, we will see that that reaction of reduction obeys the law of conservation of charge. It has 0 charge on the left and 0 charge on the right. Now, in this question over here, can you identify an equation that violates the law of conservation of charge? The equation number 1 is not doing so well with the conservation of charge because it has a charge of +2 on the left and we see a -2 on the right. The rest of the equations are doing well with the conservation of charge, but we will exclude the answers 2 and 4 because they represent reduction of elements and we are looking for oxidation half-reaction. The law of conservation of charge will help us a great deal over here. If we look at the first reaction, the left side of the equation adds up to a +3 charge, and the right side adds up to a +6. Not a correctly balanced equation. Reaction number 2 is a clear winner because it has left and right sides of the equation add up to the same numbers. This is our correct answer. For reactions 3 and 4, we see clear disbalance between the charges on the left and right side of the equation, identifying them as incorrectly balanced equations. On top of that, in reaction number 4, nickel is getting oxidized, losing electrons, but nothing is really picking them up because iron is not reduced. We see the same oxidation state on the left and right side of the reaction. Now, can you look at this question over here and identify the equation that is correctly balanced? Number 1 should be your answer. In the rest of the reactions, we see clear mismatch between the charges on the left and right side of the equations.